When I think of the worst song that's ever been written, like in the history of all humans, pretty sure it's Heartache Medication. Like, John Party, we can all agree, worst artist to ever exist. Everybody in agreement with that?
Yeah.
Okay, I actually really like that song, just for the record. Additionally, I'm going to make a comment halfway through, but we all want each other to be successful in here, yeah? Like, you want to be successful for sure. I hope you all want your classmates to be successful. You'll know why I'm referencing this here shortly, and we'll probably talk about it. But yesterday, we defined this shape. So we had a kite, which we talked about for a while, and we looked at trapezoids. We said it's a foreground with exactly one pair of opposite sides parallel. Okay, as we're looking at these, it always depends. People always get goofed up just depending on how this thing is lying. And right now, is it sitting upright or not? Like, you don't know what it is. Is that upright to you?
Yeah. Yes.
So those of you that say no, I can't wait until I draw the next one here in a minute. But check this out. The way that I lie it right now, the top and the bottom are parallel currently, the way it's sitting. We have names for these. It is weird that there's two, but when you look at the parallel sides of a trapezoid, and we're not going to make this a super formal definition, but I saw Elijah say it, we have a base right here, and we have a base right here. You could call it base 1 and base 2. If you think back to the area, you might have a little bit of it like in your memory. You take height and the sum of the bases, b1 plus b2, and then you divide it by 2 in the end. But that's not our point here. Okay. All right. So every trapezoid has two bases, and they're always going to be those parallel sides. What do we call the other sides? Legs. Check it out. We have a leg over here and a leg over here. Legs and bases. Okay. Just terminology. Now, does anybody hate the trapezoid that I've drawn?
No.
Is there a nicer trapezoid that exists? So, let me rephrase this a little bit. I'm going to give you guys like 30 seconds because I was expecting everybody to say they hated it, and I'm surprised that nobody did. Check it out. I want you to tell me if there is anything annoying about this. What is it? I want you to talk with your neighbor. Pick one of you to speak. 30 seconds. I want you to identify while the other listens what is annoying, and I'm going to ask the person that didn't talk for the answer. We have a few theorems that we're going to deal with here, and a couple of these theorems are only going to apply to special, nice, for example, trapezoids, and let's dig into those for a second. So just so you guys kind of know, we're going to talk about isosceles trapezoids right here. And then over here, if you're organizing it like mine in my notes, I'm going to put two theorems that deal with isosceles trapezoids. So it's clear that they deal with those, just so you know kind of where I'm going. So if we have a trapezoid and it's just this, what if I wanted to make it an isosceles trapezoid? Isosceles. You guys remember the shorthand for what I use for isosceles? I just use isos, I-S-O-S-C. I just don't finish the word. An isosceles trapezoid. And two what's the same, and this is a super short definition. The legs must be, so, not parallel. They can't be parallel. They would become the bases. The same, there's another word that we could use for it. Congruent legs. That's it. And I can spell congruent. Weird. All right, real quickly, we'll see why I'm mentioning this here in just a second. My favorite color is green. Just so you guys know, like, it's not really relevant, but I'll add another random thing about me here in a minute. My favorite color is green. Awesome. Okay, so if we're looking at an isosceles trapezoid, it is much more natural, and I was going to draw this really annoying, but I'll make it kind of less annoying. I think that this counts as an isosceles trapezoid. And this is the more natural one that you'd find congruent legs. And do you know, Sophia, have you seen any of these symbols that are written up here? Which if you can't see that, you probably can't see those very well either. Okay, so there's some symbols. When I write them, just make sure you ask, okay? Awesome. So for future times, if I wanted to write congruent, but I didn't want to have to write the word, how do I write that down? It's an equal sign with a tilde above it, which is like the little squiggle. Okay. So you guys don't all have to put that because you know that already. But let's see. This is G, I, A, and N. So here's our lovely trapezoid.
You didn't realize until now.
Yang, right? Clearly what I was going for. All right, so as we're looking at this, if I wanted to make an isosceles, are there any additional marks that have to be here? Dashes, for sure. Now, right off the bat, I'm going to make two claims, and I just want to see what your guts say about this. What's your intuition for these? I do not need you to draw all these pictures, okay? But I'm going to copy this one, and we're going to do a few things with it. You do not have to draw it over and over, but I want to so that I can sketch on stuff to help us think about some things. So I'm going to draw this a couple times. The first thing that I want you guys to think about, and I'm going to give you two questions that I want you to talk for like a minute or two with your neighbors and see if we can come up with these ideas just naturally, intuitively. I want to know, is there a relationship between any of these angles? So I'll write this in yellow. You don't have to put it. We're going to define a theorem, so there must be a relationship somewhere. Angles? Question mark? And I just want to know, what do you guys think is a relationship between any of the angles in here? And there's one more. Can I draw diagonals on this? How many diagonals can I draw? So I can draw one for sure. Can I draw a second?
Yes.
Okay. So here's my thoughts. I want you guys to spend a little bit of time. Is there a relationship between these angles, any relationship that you think might exist? You don't have to prove it. We'll talk about logically showing it to be true after the fact. And is there a relationship that gets made, not necessarily about these diagonals, although it might be, but do we get any new relationships when we add the diagonals in here? I'm going to give you guys like 3 minutes or so. I just want to see what your intuition. This one is an easier intuition than the other. What relationship might exist between the angles of my trapezoid, and what relationships might we get when we draw these diagonals of my trapezoid? I will give you guys 3 minutes, starting right now. I want to hear you guys. Check it out. We're going to use this picture. Any gut feelings about the angles on this? Okay, Adam, what were you going to say just in case, because I don't think everybody heard you just now, which is fine.
That G and N are congruent and I and N.
So Adeline's claiming that on this trapezoid, that we should have this be true and this be true. Anybody else have that gut feeling about it? You know what's better than gut feelings? Like, well, intuition is a gut feeling, just so you know. Justifying, like, better than a gut feeling is actually knowing it. Like, this is pretty sure it's true, right? Feels true. How would we convince somebody that doesn't believe it that it's true? That's a good point. How would we prove this is true? Liam, what'd you think?
Isosceles theorem.
The isosceles theorem. That deals with triangles, doesn't it?
I thought that was the base angle.
So it's the base angles of an isosceles triangle. But hold on here. Hold on a second. I'm just going to take this off. So there's two ways. Now, on this one, and I heard Elijah say this, I could make it a triangle with the top chopped off. Right? Like now it's a triangle, and I'm pretty sure that this side's going to be the same. Did I just say I'm confident 100% that those are the same?
No.
No. So maybe there's a different way we could go about it.
Oh, the other one. The legs are congruent. Those two are isosceles triangles. Those two are.
I'm going to give you guys a hint, and then we're going to do the thing. We're going to start trying to do more of this back and forth where you pair up, and then I have you guys share after talking, so we don't just get, the same people answering. But what I'm encountering, not as much in this class, which I appreciate the heck out of it, is in a lot of my other classes, I ask a question, and then I just wait for like 30 seconds, and it's really awkward for everybody. So instead of doing that, I'm just going to do more of this turn, talk to your neighbor, and then we'll come back together stuff, which means you need to help me be more diligent about resuming when I unpause. My favorite number is 7. My favorite color was, don't say it super loud, favorite color? Favorite number?
7.
Okay, cool. All right, now looking at this, I want you guys, we're going to add an auxiliary line to this. We're not going to write a formal proof unless somebody's like really wants to do that right now. I care so much more about the logical steps than the writing the physical proof. Way more important. Okay, anybody recall what an auxiliary line is? Okay, we only used it in 1 or 2 proofs. If I can add lines to this that don't really change it, but just help me think about it differently, that's an auxiliary line. I'm going to add an auxiliary line to this, and there's a couple ways we can do it. I'm going to add this one, and I'm going to add this one. And we don't have to name these, especially if you're not looking at this. I'm going to call this S and T, just so that we have new letters. With these yellow lines, could you convince me that I and A are the same? I'm going to give you 60 to 90 seconds, and we're going to like hold tight to that this time. Talk with your neighbors. How does adding these lines allow me to guarantee that that and that have to be the same? I will give you a moment. Go. Now, I want to chat real quick because more than one person might have come up with this, but I'm going to highlight Chelsea had an awesome idea with this. And it's not exactly what we're going to do, but I do just want to celebrate. It's a super cool idea. What Chelsea is doing, and Chelsea and Jonah, I think, came up with this, is they're envisioning this shape changing. And that specifically, if we were to cut this part off and like physically pick it up and move it and rotate it and put it here, it would fit, right? It looks like it should fit. Now, we can't do that because we don't have the math to really knock that out. But I'm going to answer the same question in just a little bit different of a way. If we could show that this triangle is congruent to this one, A and I would match, right? How could we show that those two triangles are congruent is essentially the new question. Right now, we already have a leg congruent to a leg. Ooh. So that's actually not a leg, I'm sorry, a leg of the trapezoid. This is the isosceles of that right triangle. Why do you think that this is the same as this, though?
Just the perpendicular distance between parallel lines is the same.
Love that. When we talked about parallel, there's a couple different ways you can think about it. We saw parallel means two lines that never meet. That's one way we can interpret what parallel means. I'm cool with that. That happens. Another way is two lines that have the same slope. Fine and dandy. That's not what we're caring about here, though. The last way to do this and to define parallel, and if you look back in your notes, you'll see it. If I measured this distance, to stay consistent, we do it perpendicular. I have to make right angle to one of them. If I measure this distance, and I'm just going to make it up, it's 5. I'm pretending right now. It actually is 5 grids on my square, too, so that works out well. If this distance is 5, what's this distance?
5.
And this distance?
5.
And here?
5.
And here?
5.
So if that's 5, that's 5. That is for sure the same length. That is hypotenuse leg is what we have now. Can I now convince you that those triangles are the same? And it would be triangle IGS matches up with what? A and T. A and I would match at this point, and we would conclude then that, yep, I and A are congruent. So I'm going to get rid of these yellow dashes, and I want to go one step further. If I know that these are the same, do I know that these are the same? How, Sonny?
Just like you said, hypotenuse leg. It's isosceles trapezoid, so he just assumed here.
Ooh, what happens when we assume?
Yeah, there you go.
All right, so we can, but it's way easier than that. Check it out. What are the bases of a trapezoid, just by definition? We say the bases are the sides that are. So I stopped so we could see the trapezoid, but is this still parallel to this? Are they cut by a transversal? These are both, I'll make that one nicer. Is this angle and this angle on the same side? So interior, sorry. Or same side of the transversal. What do the same side or consecutive interior angles always add up to between parallel lines? So whatever this is, I'm going to call it x for now. 1 arc plus x is 180, right? Well, good thing we have, I'm going to put that back as x temporarily. And check it, we have another parallel lines cut by this transversal. This 1 arc plus this had better add up to, has to be x also. We're there, they have to be the same. Now, we just did a full proof, we just didn't write it as A, B, C. Logically, and pure honesty is all I'm after, if it's not at all, you probably don't want to do this and say, hey look everybody, I don't get it. But logically, could you follow what we did on that proof? Thumbs up says, yep, I can follow everything that we did there. Thumbs down, I don't know what's going on. Anywhere in between. Where would you put yourself? Okay, so I do want to stress, and I'm broken record with this. I don't know if that joke really landed with you guys or not. Klein, I am so thirsty. Will you go give me a drink? Cool. Awesome. When can you come talk to me for struggle with stuff? Before or after? Now, we're going to have a little bit of time to work on homework in a minute. Let's get this theorem written first. Our first theorem dealing with these. I have no idea what number we're on. 6.4? Theorem 6.4. And remember, there's two of them that are going to happen here. Theorem 6.4, is it what?
I think we skipped 6.2.
It's probably in the first section. That's okay, we'll call this 6.4. We're going to talk about the base angles of a trapezoid. Base angles of... Klein, I thought you were going to give me a drink. Cool. I'm parched. Check it out. Instead of a big if-then statement, I suggest that we use just our nice implies arrow. If you give me an isosceles trapezoid, and I'm just going to write it there. If you start with an isosceles trapezoid, then, what do we just say we're congruent? The base angles. Both pairs of base angles, specifically. Both pairs of base angles congruent. Now, this is the fewest word that we can possibly write this theorem. And just as a reminder, because it's been a while, when I see this crazy arrow, what's the word that goes in front of this? If it's an isosceles trapezoid, in this we would read how? Then or implies. Then both pairs of these base angles are congruent. Okay, as an e.g., since we all have the same picture and it probably doesn't have all the lines and I got rid of stuff, e.g., exempli gratia in Latin, remember, it's just like, hey, let me demonstrate. What's congruent on this one to angle I? I is congruent to not G, A, but you might have been saying the other thing, and I'll use the word and rather than our fancy one. What's the other one? G is congruent to N. Okay, there's our first theorem. This one, did we have anything come out of it? Any intuitions? And I'm just going to check rather than saying, did we have any? How many of you guys were able to start talking a little bit about these ones? Okay, this one we're going to hold true. 30 seconds. What do you think might we get when we draw these diagonals? Another theorem is going to pop out. What is the relationship between them? 30 seconds from now, talk. Five, 4, 3, 2, 1. All right, give me some ideas. I'm going to write them down up here. We don't need to write them all down until we decide which ones are really true. What do you guys think happens when we draw these diagonals? Two congruent, just two? Okay. Two congruent triangles. Where's, maybe, okay, I see what you're saying. So I'm just going to put it, two isosceles, and I'm not confirming or denying either of these, just so you know. Anything else?
Triangles that overlap.
So there's certainly some overlapping triangles. What if I make this? What if I claim, and I'm just looking at this one, is IN congruent to anything? GA. Do you think that's true, or does it just look true? I mean, it certainly looks true. Huh. All right, so let's dig into this one a little bit. I'm not going to go as hardcore through this proof, Sevia, so don't worry too much. But I'm going to make this a little bit easier. There's a lot of triangles. Like, way more than you probably just look at first. I'm not going to make you count them. But here's what I'm going to do just to make this a little bit easier. I'm going to envision that we're going to take this thing apart. And we happen to have some overlap. Could I take just this part out? GIA. So let me do that real quick. And I'm just going to draw, and it's not going to be perfect. But here's triangle GIA. And it's not the same scale, but there's G and I and A. And we had a dash here, right? Cool. Can I do the same thing with this, this triangle? And if I did it, and it's weird because I'm going to have that defined twice, but I'm just taking them apart as if they would slide together. This still has a dash. That'd be N and G, and A would be here now. Just so you can see, it doesn't have the top on it, but if I did physically move this, that's that trapezoid, right? I'm just viewing it so I can see these very clearly. Now, if I do this, let's just think, is there a side that's the same on both of them? IA is on both of them. And then what did we just decide was true about angle I and angle A? So what's true about these triangles? They must be congruent. Side, angle, side. Is this going to be the same as this then?
Yes.
Guaranteed. Now we do get some other stuff out of it about congruent triangles. This triangle ultimately will be congruent to this and so forth. There might be some other ones we could pick out, but this is the one that I care the most about that we're going to use to write theorem 6.5. So again, it only applies to isosceles triangles. Let's make this a theorem. So theorem 6.5, knock it out real quick. And I'll switch color just so we can see it. And then we'll do a quick vocab brain break, if you guys would like. Theorem 6.5, and we're just going to say diagonals, and I'm going to write the whole word, I lied. Diagonals of isosceles trapezoid. Okay, now this one, I'm going to let you guys help me decide. We can write it as if it's an isosceles trapezoid, or we can just work with the assumption that that's where we're at because we've already written the diagonals of isosceles trapezoid. What did we just say was true about these two? So, yeah, go again. The diagonals are congruent. And I'm going to use my fancy equal with that tilde here, and a quick EG just to make sure we have it. IN guaranteed is congruent to what? GA. I'm going to call it AG just so that my order feels more consistent, but GA is also acceptable. Cool. We use this, and it's hard to see unless you physically take these two triangles out. But once we take them apart and really view it, I hope it became much more clear that those triangles were the same. All right. Other things I heard this morning when I taught this first, a lot of people wanted to say that these two were the same. They're not. It depends on how you draw it. Like, you can draw it such that it does happen, but it is not guaranteed ever. Okay, do these feel okay? These two theorems. Okay, do you want a vocab brain break real quick? I also have one other thing that I'm going to show you. Okay, so first thing. Yep, we're just going to stop it there. I don't know what it is. Okay, these theorems. What type of trapezoid do those two theorems apply to? Only isosceles. Are there trapezoids that aren't isosceles?
Yeah.
Yes. So we get one more theorem out of this, and we're going to specify, we're just going to give us a theorem, and then I'm going to give you guys a little bit of time to work on stuff. I know that we didn't do a ton of examples. If the homework goes poorly, we'll use that time tomorrow when we discover that to work some examples together. But I don't think that just the theorems are crazy to apply. If I'm wrong, and we'll fix it. But let's look. Last theorem of the day. So here we go. Theorem 6.6. We're getting close. Okay, first thing. How many sides does a trapezoid have? 4. What do you call the sides that aren't the bases? Legs. And they have a length, right? Do you think there's a midpoint on each of those legs? Yeah. So we've never seen this word, but I'm going to give ourselves this theorem, but I'm also going to introduce a new word and just try to do it pretty quickly. We're going to call this the mid-segment theorem. What do you think, and just go way out here, what do you think the mid-segment might connect on a trapezoid? The midpoints of the legs. So we'll just sneak that in here. Theorem, sorry. The segment connecting, or just connects, the midpoints I'm so sorry. I will write bigger, Sophia. Keep reminding me, okay? My bad. Connect midpoint of legs. Okay. So we're just going to draw this one out because it's going to be way quicker than the verbal vomit that we'll have to work out to get it to write it in a nice sentence. All right. I really want to draw an annoying trapezoid, so I will. Okay. Oh, it's so awesome. So here's a trapezoid. It's a trapezoid. It's not as annoying as I wanted it to be. Here's a trapezoid. It's beautiful. And we'll call this thing YASH. Cool. So we have Yash the trapezoid hanging out here. Love it. What are the legs of this trapezoid? YH and AS. And they both have a length, right? Okay. So when I'm just going to eyeball this, but we could go through and actually find the midpoint. Do you guys believe it's about here? Okay. I believe it's about there also. Okay. I'm going to name these. Nobody in here has a 2-letter name. Huh. Tie. What? It depends on the tie you spell. We'll call this X and Y. I don't really care what they are. We'll call this X and Z. Thank you. If I wanted to make a mid-segment on this trapezoid, J-Man, that's Jonah, by the way. Are you the only person with J as your first letter in here? Okay. What would you connect if you wanted to make a mid-segment? Which 2 points? Love it. The 2 midpoints. Okay. We're going to do a quick little thing. Same thing. I'm going to call 2 random people here. X and Z, this is my mid-segment. You are correct. And if you want to write it, we can. That's my mid-segment. I know the writing's really small. It just says mid-segment. All right, so let's check. I want the first thing that you think might be true about it. Number 1, who dat? Number 8, who dat? I need to go just get my list. Ronaldo, what do you think might be true about this? And that's all I'm giving you. AZ. So definitely. So I agree with that. I'm not going to write that one down, but you're right. These are the midpoints. So definitely that and that are the same, and that are the same. I'm going to be more specific. Don't just give me that one. How about number 20? Just kidding. 5. Just 5. Who's 5? Okay, Jonah. Any gut feeling? What do you think this might be with relation to these? If we extended this one out forever and this one out forever, they'll never touch. Love it. Anybody else think that this is probably parallel? It is. I'm going to give that one to you for free. Our theorem that we're looking at, the midpoint, the mid-segment here. We're just going to write our theorem. The mid-segment. And notice, are we talking about an isosceles trapezoid right here? Or is it just a trapezoid? It's not an isosceles at all. It's a goofy looking one. The mid-segment of any trapezoid, and I'm just going to call it a trap because that's faster, is, and we're going to have 2 statements. The first one, Jonah's intuition, and many of your intuition, I hope, was correct. First one, parallel to the bases. This will always be the case. If you give me the mid-segment of any trapezoid, it's always parallel. The second one is not as natural to feel. We're going to say the length of the mid-segment. And do I have to say length of mid-segment, or is it clear that we say the mid-segment of any trap is length equal? Is it clear that I'm talking about the length of the mid-segment? Yeah. Okay. The length of every mid-segment is simply going to be 1/2 times the sum of the bases. Now, the parallel part, I'm not even going to bother writing with the EG. I think it's clear. XZ is parallel to YA and those two. The other part, though, we are just going to write the EG for it, and I'll switch color so it stands out a little bit. It's up to you if you write it. What this second part of the theorem tells me is if I wanted to find the length of, in our picture, it'd be XZ, it would be 1/2 of what two things added up? Yeah? And I can have a noise for this one. SH. Every mid-segment is just half the sum of the bases. If you think back to the formula for this, maybe it relates back to that idea somewhere along the way. Okay, we're going to try something we don't normally do. We didn't really do any true examples today. Now, we especially didn't write any down. We did do a lot of mathematics, though. We did a lot of talking about the logic. It was just more verbal than physically writing down today. If this is a bad idea, we'll learn about it tomorrow. But I'm going to give you an assignment now, and I want you to try it using these theorems that we've talked about today and yesterday. So, your assignment today, I'm pretty sure I put it on this one. Let me I'll just copy it. Your assignment for this evening is going to be this. Homework 6.2. You will find this on page 264. And I want you guys to do problems 14 through 20. Okay, just as a reminder, if you're crying about math, it should be tears of joy. How long should you spend on this outside of class? 30 minutes. If you get to 30 or 40, I'm going to trust your judgment. Did we talk about homework expectations in college and stuff yesterday?
This morning.
I talked about it in another class yesterday also. We'll save that one for tomorrow. Cool. 30 or 40 minutes. I don't want you to stay up all night because you're working on the assignment. If it takes longer than that, just come talk to me. There's something that we should clear up to make it go faster. I'll be around for a few minutes. You guys can get a quick start on it. We have like 4 minutes left of class. I'm going to step outside because I want to show you guys something cool.
Oh.
Cool.